Hello everyone. I hope you enjoyed the 8 weeks course on medical biomaterials. So it covered quite a lot of topics related to metals, polymers, ceramics, and so on. And I hope you enjoyed the course. You learned a few important points, and then you were able to answer some of those weekly quizzes. And we also had a few experimental demonstrations where we tried to show how to make polymer with different morphologies like films, hydrogels, nanoparticles, electrospin, and so on. Okay, so I think those experiments also would have been very useful for you during the course of the learning process. You will also would have come across many instruments and equipments needed for performing the various tasks. So you understand the level of complexity involved when you are planning to design a biomaterial. I thought I will show you initially a few samples of biomaterials. Okay, this is a stent. Okay, can you see this? This is a stent. This is a vascular stent. It's made up of titanium, and it's a larger diameter. Whereas if you look at a cardiac stent, it will be of 1 mm, 2 mm diameter, whereas these vascular stents are of larger diameter, and they're also made of titanium. And this is the white one, as you can see, is a polyurethane ureteral stent. This is used in the ureter so that the urine flows down into the bladder, especially if there is an obstruction in the ureter because of infection or stone. And this particular ureteral stent is used. Can you see this? So this is made up of polyurethane. It's flexible. Okay, it's called a pigtail, double J stent, and so on because of the shape here. Let me show another polymeric material. This you can see this at the bottom here. This is a vascular graft. This is polyester-based vascular graft. This is about 5 mm diameter. It's made up of polyester, stretchable vascular graft. And if you want to go for smaller diameter, then they go into PTFE, polytetrafluoroethylene, ePTFE, expanded PTFE. So those type of grafts are used if you are going for smaller diameter. This is a implant, metal implant, titanium metal implant, as you can see here. Okay, it's got a lot of holes so that you can fix it to the bones here. You can make it with stainless steel. Okay. And you can have different dimensions, different sizes of these implants. Okay, and I want to show you something like this is a drug delivery system, especially used in orthopedic situation. Actually, this is a drug delivery system. It's made up of polymethyl methacrylate drug delivery. So the drug gets delivered, and after that the polymer has to be removed. So it's made up of PMMA, polymethyl methacrylate. Okay, and this is the hydrogel surgical dressing, especially for surface wounds. Okay. As you can see, this is made up of polyvinyl alcohol. This is a commercial product. Okay, it can retain a lot of water, and hence it's used quite a lot. These are some material used for dental applications. I'll show you one dental application. As you can see here, this is a drug-loaded collagen. So especially for periodontal infection, so they fill this collagen with drug and fill up the periodontal space. So the drug gets released and infection goes away. Okay, and this is a calcium sulfate hemihydrate. Calcium sulfate hemihydrate. It's quite a lot used in orthopedic, where you can make beads out of it and fill up with allografts so that the gap is filled, as well as you can fill it up with some antibiotics so that the infection doesn't happen. So a lot of biomaterials, polymeric metals, ceramics are used, and sometimes combinations thereof You modify the surfaces of some of these to achieve a good biocompatibility, antibacterial action, and so on. Okay, so it's a very exciting field, and let's spend some time on what we have been looking at over the past 8-week course. Okay. Okay, so we looked at a lot of material. So the definition of a biomaterial is any substance, it could be synthetic or natural, because a lot of biopolymers like glucon, hyaluronic acid, all these are used. That is why it's called natural also. Whereas synthetic, metals, polyesters, polylactic acid, they're all synthetic. Combination used for some time. It could be for a very short duration, or it could be for life. For example, if it's a cardiovascular stent for the rest of the life. If it's a bone replacement, knee replacement, if it's a long segmental defect, it's for life. Okay, so it can vary from a urinary catheter for a few hours, going right up to months, years, and lifelong. Part of the human system. It treats defects, augments, because there is something called a left ventricle assist device, so it augments. Then diagnosis, you can have biosensors, or it replaces tissues. Okay, it can replace any part of your tissue, skins, organs, functions of the body. All these, that's the definition of a biomaterial. So drug is not considered as biomaterial. A lot of materials are nowadays used as biomaterials, and there is a lot of interdisciplinary research which involves material scientists, material engineers, clinicians, biochemists, polymer chemists, all coming together to design novel materials which are smart, as they are called actually. So we use a lot of material in our body: dental implants, polymethyl methacrylate, titanium screws, stainless steel, acrylic acids, fillers, tooth fillings, cardio and vascular implants. Okay, a lot of polyesters, PTFEs, titanium, nickel, drug delivery systems. Okay, polymethyl methacrylate, polylactic acid, bone fixing sutures. Originally nylon sutures were used. Nowadays biodegradable sutures are used. Bone defect filling. If there is a defect because of an infection, or because some problem has happened in the bone after a trauma, it's filled with calcium sulfate, hemihydrate, it's filled with allografts, it's filled with biodegradable polymer. Hip joint processes. Nowadays, the hip joints are completely replaced. So you have metal polymer situations, bone plate, titanium bone plates, stainless steel bone plates, scaffolds for tissue engineering, different types of polymers, PLG, PLA, which are biodegradable over a period of time, so that the cells start growing. Contact lenses. Okay, it's extremely hydrophilic type of material, HEMA as it's called. Right? That polymer is hydrophilic, has got good oxygen permeability. Catheters, different types of catheters, urinary catheters, which stays for a very short period, made up of polypropylene, blood bags, urinary bags, so on actually. So lot of biomaterials are used in our body. Now, if you look at the market, it's a huge market. 2020, it's predicted to be 130 billion US dollars. That's a very big market. Even in India, the biomaterial market is growing a lot because of cardiovascular surgery, and then because of the knee replacement surgery, bone additions like metal plates after a trauma, and so on actually. So even in India, the market is growing very large. So if you look at the biomaterials market, the biggest, based on application, biggest is all related to cardiovascular. You have the stents, okay, and then we have the shunts, we have the diaphragm valves, we have the vascular grafts, we have the patches. So a lot of cardiovascular application. Then comes orthopedic bone, things like bone plates, okay, bone screws, wires, knee replacement surgery, and so on. Then comes dental. Dental is all related to tooth filling, periodontia, addition of artificial tooth, changes in jaw, plastic surgery. Of course, there is a relationship between dental and plastic. Then wound healing, surface wounds, antibacterial, anti-inflammatory, different types of wound, diabetic wound, wound after burn wounds, and so on. Then neurology. This is going to be a challenging area. So not much research is done so far, but this is going to be the future. Tissue engineering, artificially creating various organs, various tissues, and then implanting them after allowing it to grow outside. Then ophthalmology, replacement of some of the parts in the eye. If you look at the biomaterial markets based on the material, metallic, of course, comes in the top. Stainless steel, titanium, cobalt, chromium, nickel, all these are metallic biomaterials. Ceramics, hydroxyapatite, calcium-based products, calcium sulfate, calcium phosphate, silica, that is bioglass. Then comes polymer. Actually, polymers seem to be third, but polymers find their places in both metallic and ceramic. Different types of synthetic polymers. Sometimes many metallic systems are coated with different types of polymers. So polymers, although it appears to be third, it is part of 1 and 2 very much. Then natural biomaterials. Okay, these are not much used nowadays, but mostly these are the things, combinations of these three things are used so that you are able to tailor the property, you are able to tailor the physical-chemical biodegradation property and toxicity and so on actually. Okay. So what are the problems? Because these biomaterials are going to be part of the human system for short or very long duration, we need to consider toxicity, cytotoxicity. Okay, short-term toxicity, long-term toxicity. Then you have the metal toxicity, because if you have metal leaching from joints, then sensitization because of nickel. Some patients are toxic to nickel, so they go and accumulate in body tissues, and that leads to inflammation. Then we have genotoxicity, carcinogenicity, reproductive, developmental, neurotoxicity, immunotoxicity, and so on actually. So a large number of toxicities are associated with the biomaterials. So although biocompatibility is only one part, which we generally look at in the early stages or initial stages of the biomaterial, we need to consider all these types of toxicities as we go along, because some of the biomaterials may be passive, but some of them are active, leaching out metals and so on actually. So we need to consider all these aspects as well, short-term as well as long-term toxicity. Okay, if you look at the biomaterial history, we had first generation biomaterials, second generation biomaterials, third generation, and we are going to move towards fourth generation. So early 50s, the clinicians, the surgeons just put in some inert material into the body. So they put wood. They thought biomaterial has to be inert, it should not cause any in the human system. So they used natural materials. They used materials like wood, they used materials like ivory, metals, and so on. They just fixed it, especially in teeth or even after an orthopedic operation. But then they realized that inert materials are really not good. The material has to be active. That means it should help the wound to heal. It should help the material to get absorbed. Then came the second generation. They are called bioactive, bioresorbable biomaterials. Okay, so HA, polycaprolactone, PLGA, collagen. So many of them degrade. That's why they are called bioresorbable. Then bioceramics, Okay, this BG means bioglass. So it has to be active. It should help the tissues surrounding to grow in a natural way, unlike this bio-inert material, and that was called second generation biomaterial. Okay, then we went into nano systems, nano composites. Okay, nano HA, because as you know, nano material has higher surface area, so the tissue ingrowth was always good. So tissue ingrowth, tissue development, growth, all those was very nice. So you had a very bioactive, highly bioactive system, and of course they also HA will get absorbed into the tissues, whereas the polymer support will completely get bioresorbed, like polylactic or polylactic glycolic acid. Okay, so that came in the late 90s and early 2000. Then off late, there is a lot of interest on this biomimetic materials. Okay, that is materials which mimic the natural systems. Okay, so collagen, cellular, biological molecules. So can we coat with biological molecules so that the host response does not start getting activated. Okay, so that's called a tissue engineered scaffolds. So you grow the tissues, grow the cells externally, seed the cells externally on certain scaffolds which are biodegradable, then insert the scaffold into the body. The tissues would have grown partially, and slowly the support starts degrading. Okay, so they are called biomimetic biomaterial. So that's where it's going, and they want to introduce smart materials where the materials change its properties based on the conditions, which can be pH or temperature or other physicochemical parameters changes. So the smart material concept has started coming into this fourth generation, and so ultimately you are going to have such smart biomaterials which will be engineered and which will be biodegradable after a period of time once it has done its job. So this is how the biomaterial scenario has changed over the past 60 years, starting right from a bio-inert, going right up to smart, intelligent biomaterials, which can think on its own. So we did a lot of things during the course. We looked at metals, properties of metals, crystallinity of metals, force, stress, strain, modulus. We compared different metals, and then we compared metals with the non-metals, and so on. Synthetic natural blends. We talked about polymers, and then we came to ceramics like hydroxyapatite, calcium phosphate, calcium sulfate. So we looked at combinations of ceramics with the polymers. We coated metals with polymers. We looked at those. Then that is what is called composites. And then in the polymer, we also looked at many different types of polymers, synthetic polymers like PLA, PLGA, PET, PVP, LDP, whereas natural, we looked at glucons, cyclodextrins, gelatin, and so on. Okay, so we did a lot of these combinations. We looked at their properties, how to tailor their properties, how to modify the surfaces to make it more antibacterial, less cytotoxic, how to improve biodegradability, and all those things we studied. Later on, okay, so we looked at morphologies, because sometimes biomaterials will be in a beads form, nanoparticle size form, like a film, like a hydrogel, like a electrospin mat, thin fibers. So the morphologies, and nowadays there is a lot of interest on 3D scaffolds. So the morphologies changes. So we should have facilities to design different morphologies, not just one type of morphology, depending upon the application. I have reconstruction surgery because of some trauma in my bone. I want to fill that, so I will require a different morphology of biomaterial. I am talking about a wound dressing, then I will require a different morphology of the same biomaterial. If I'm doing a drug delivery, then obviously I need to have a different morphology. So, and then the surface modification, so that you make the surface less cytotoxic, less less bacterial attachment. That means it becomes more antibacterial. So all those morphologies changes. If there are some biomaterials which are used in cardiac and blood contacting regions, then it should not cause certain responses and allow thrombosis to form. Okay, so that is another situation we need to look at actually. Then we looked at material blood cell interaction. What are the various stages happening during this process? What is the coagulation that's happening? All those things we looked at. And then we looked at tools. There are hundreds and hundreds of tools because as you can see, this is a highly interdisciplinary area. There are a large number of tools related to mechanical engineering, stress for measuring strength, for measuring wear, for measuring stability. Then polymer related tools, which looks at physicochemical properties, which looks at the characterization of the material. Then there were tools which look at the contact between biological system and the material. And then we had microscopy, which looks at the morphology changes of the bacteria, cells when it gets attached. So we looked at all the types of tools in a very brief manner, of course, because you can spend a lot of time on the tools. Okay. There is one question whether these biomaterials can be used in pharmaceutical. Yes, drug delivery is becoming a very important area of late, where if I want to have a targeted drug delivery, or if I want to improve the GI absorption, or if I want to improve the bioavailability, so I need to encapsulate the drug using a polymeric system, so it is able to travel through the GI and reach the target site. So the drug delivery is one area where I think pharmaceutical industries will definitely benefit from that. So when we design a drug delivery system made up of a biodegradable polymer, we need to consider all these aspects: the stability of the material, the cytotoxicity of the material, how it degrades, how the drug gets released, the release profile. There are now interests on having a delivery of two drugs. You can have a fast-acting antibiotic, and then you can have a slow-acting antibiotic, both delivered to the target site. We can have an antibiotic and anti-inflammatory drug delivered at a site, especially. So the antibiotic will prevent the biofilm formation, whereas the anti-inflammatory type of drug will help in the growth of the tissue. So drug delivery is one area where biomaterial knowledge will definitely help the pharmaceutical industries. And of course, we have things like wound dressings, burn wound dressings, and diabetic wound dressings, where drug is encapsulated in the dressing, and slowly it gets released. It prevents the bacterial attachment. At the same time, it's got a very high level of hydrophilicity. That means water retaining capacity, and it also permits oxygen to flow through. So wound dressings is another area where I think pharmaceutical industries can enhance their products so that they can develop wound dressings for diabetic wounds as well as for burn wounds and so on. Actually. Okay, I just want to show a few pictures where these biomaterials have been used in different applications. For example, this is a heart valve. You can see this titanium cobalt alloy, and then we have the polyester, polytetrafluoroethylene, polypropylene. These are non-biodegradable, very strong, because this heart valve has to work for the rest of the life of the patient, right? So they are all very stable polymers, they remain. And of course, titanium, cobalt also remain for the rest of the body, rest of the life of the human patient. So you can see it's a combination of several polymers. So it has to work for the rest of the life of the patient. This is a poly-L-lactic acid. Okay, this is a biodegradable polymer. Okay, so it's used in the ligament, and it keeps the ligaments together. and once the ligaments automatically join on its own, by the time this polymer also would have degraded. Look at this. This is a titanium plate here, and they also keep with a PMMA spacer. Okay, so there is a gap here. So you have a PMMA spacer here, which is kept here. Sorry. So PMMA is non-biodegradable, so it will remain forever. Antibiotic loaded PMMA beads. Okay, so you load meropenem, a broad spectrum antibiotic onto this PMMA, and when there is an open wound because of an orthopedic accident, so these beads are kept inside and stitched, and as the drug gets released, it prevents the bacterial infection at this place. Later on, these beads have to be removed because PMMA is not biodegradable. So there is a lot of interest in developing polymers which are biodegradable, at the same time are able to have a lot of drug encapsulated, PLA for example, or PLGA, and so on. These are ureteral stents. I showed you some time back. These are made up of polyurethane. They are called pigtail or double JJ because JJ. This is made up of polyurethane. Originally, they were made up of silicone. Silicone is sort of the gold standard, but it's a bit irritating, whereas polyurethane is highly flexible. So it is used. As you can see the X-ray picture here, it is kept inside. So the urine flows through the ureter, comes down to the bladder, and this is used if there is a blockage in this region because of infection or stone blocking. Generally, this is kept in place for 4 to 6 weeks. Once the infection is gone, this can be taken out here. And there are many problems with these ureteral stents. You can have salt deposition like calcium, magnesium, oxalates. You can have E. coli, Proteus mirabilis also attaching to that because urine has all these organisms also. So those are some problems which needs to be addressed in these type of stents. These are PLGA type of ureteral stents. The beauty of them is these are biodegradable, unlike the PU. So you do not have to remove this, but then still the degradation has to be more uniform throughout rather than at different places. Then the stent may break at different places, and then the problem could be how to remove them, and you need to perform an operation. So that's one problem here. Look at this. These are all in cardiac region. Okay, this is a BT shunt. This is made up of polytetrafluoroethylene. So it is placed here, right in the aortic branch and pulmonary artery. So if there is a hole in the heart, the blood, the bad blood, instead of going to the lungs, gets short-circuited and goes to aorta, and then it goes to the rest of the body. So the blood will be sort of blue in color, whereas if it is well oxygenated, it will be red in color. So these BT shunts are placed like this, so that blood is pushed into the artery to the lungs, so they get oxygenated. These are made up of PTFE, polytetrafluoroethylene. These are generally given to pediatric patients because children born with a hole in their heart. That means some of these are connected here. Some of these chambers are connected here because they are not fully formed. This is an angiogram of the same thing. You can see here. This is the angiogram of this. These are kept in pediatric patients because it's very difficult at that age to do an open heart surgery and close the gap between the various chambers. Once the child grows to a sufficient age, they will make an open heart surgery and close those holes. So these are made up of polytetrafluoroethylene. Okay, look at this. These are knee replacement systems. This is polyethylene, high cross-linked, high density polyethylene, and then you will have a chromium nickel type of thing. So it goes round and round. This polyethylene keeps the metal on metal, prevents the metal on metal contact. Otherwise, when you have metal on metal contact, sometimes cobalt, chromium starts getting leached out, and it could be toxic to some patients. Some patients have toxicity, nickel toxicity, and this nickel may be getting accumulated leading to inflammation and other problems. Okay. So that is why this high density polyethylene is placed here in between the two metals. Again, this is the same thing, ureteral stent here, which helps the urine to flow through the ureter. Okay, so there are a lot of biofilm that forms on this stent, okay, because one is salt deposition and then the bacterial which gets accumulated, which is found in the urine. These are some hydrogels, as you can see, these are 3D network hydrogels. Hydrogels can be made with many different types of polymer, polyvinyl alcohol, okay, and glucons. They can absorb, retain significant amount of water, more than 150%. It's got a lot of hydrophilic groups. Okay, so these are used quite a lot in wound disease situation. These are stainless steel bone plates. Okay, as you can see, you have the bone here, you keep the plate here, and then we put screws here. It can be a metal screws or it can be a polylactic acid type of screws. Okay, so stainless steel is cheaper, but the problem with stainless steel is it's got high modulus, as well as bacterial contamination can happen, as well as corrosion of stainless steel is a problem. So they are moved towards titanium based material because corrosion does not happen, but still you can have bacterial infection. Titanium has lower modulus than stainless steel, but still the modulus is higher than the bone. That's a problem. But nowadays there is some interest in magnesium. Magnesium has many advantages. It is biodegradable. Its modulus is comparable to bone. Okay, and so there is interest. But the problem with magnesium is the biodegradation is very high. So we have to sort of slow down the biodegradation of magnesium so that it doesn't degrade too much. So these plates are used in the bone defects region. So you can see some of these stainless steel bones coated with silver nitrate and lactic acid. Polylactic acid degrades slowly. Silver nitrate, as you know, is antibacterial. This is uncoated, this is coated. So you can see the bacterial adhesion is less on a coated surface as against, because silver nitrate is a good antibacterial material. These are, as I said, these are titanium bone plates. You can see here titanium bone plates. Again, you have the bone, plates are kept here, and you have screws here. So the bone starts growing here. Okay, you can again see it here actually. Okay. Ceramics, there's a lot of interest. Hydroxyapatite, calcium sulfate, calcium phosphate, bioglass. Okay, because our bone contains hydroxyapatite and collagen, right? So there is a lot of interest. As you can see, calcium sulfate. So if there is a defect here in the bone because of infection or because of trauma, all you have to do is you need to fill it up with this type of calcium sulfate here. You can take some allografts and fill it up, and it heals very well. So there is a lot of interest in bioceramics. Okay, so we have spent 8 weeks on the fundamentals, but if somebody wants to go into basic research, I thought I'll give you a list of areas which are going to be the hot in the next coming decade, actually. Okay, so calcium phosphate, like I said, the ceramics is a big area in many applications. So tailoring the property, calcium phosphate, tailoring the property, because it's got very poor mechanical property. So can we tailor the property? That is one big area. Okay. Then sutureless method for joining blood vessels. So instead of using originally non-biodegradable sutures were used, then came biodegradable sutures. Now can we use some other method? Glues. There is a lot of interest nowadays on glues. Even clips okay, are coming into whether we can join blood vessels without any sutures. Okay. like a glue. Smart materials, okay, materials which can change shape depending upon a certain environmental condition, change its properties, change its morphology, new materials. So there is a lot of interest in these type of materials, which will expand on its own or even contract, change some of its physical chemical properties. And so that's called smart materials. Injectable biomaterial. So why do I need to open up the body and then perform the operation and then close, which can lead into a lot of infection and then recovery? So can we make a small hole and then inject our biomaterial to it? Can we make the, say, calcium based material like a toothpaste? Then you just inject it into by just creating a small hole. So that way we can reduce the recovery time, we can reduce the operation time for the patient, we can prevent major infection. So injectable biomaterials is one area which is going to happen. This can be used for orthopedic situations, it can be used for facial reconstruction, cranial reconstruction, and so on. Actually, injectable biomaterials. Biodegradable metals, like I said, magnesium, but then it has got some problems like fast biodegradability and hydrogen release. So can we have more of this? Biodegradable metals. Microfluidics is one area which can be used for synthesizing new particles of different morphology, generated polymer microparticles. Can use these type of techniques. Neuronal biomaterials. Most of the biomaterials, if you see, related to cardiovascular, orthopedic, dental, but there is very little neuronal biomaterial. So there is going to be more research in this particular area of neuronal biomaterials. Biopolymers, novel biopolymers, because as you know, biopolymers are anyway biocompatible, less cytotoxic. So that is one area that will also grow, but it will not be used on its own. It will be blended with other polymers to improve certain properties. So biopolymers is another area. Balloon catheters. So catheters, certain modifications using balloon catheters, direct sensing electrodes, biosensors, novel biosensors. We want to measure everything in the and then transmit it to outside so that the patient can be monitored continuously. So direct sensing electrodes, biosensors, this is one area that's going to grow quite a lot in the future. Aesthetic appearance, of course, this has always been there for past thousands of years. So cosmetic surgery, I think biomaterials, especially facial reconstruction, orthodontic applications, dental applications, all have certain inner reason to improve the cosmetic appearance of the patient. The laser processing of biomaterials. Can we modify the surfaces, make it more biomimetic, blood compatible, more biocompatible? So that is another area which is going to grow. 3D printing. Can we print or prepare vascular grafts? Can we prepare certain implants? Can we prepare certain different types of scaffolds using 3D printing? That's one area which is going to grow quite a lot in the tissue regeneration, tissue engineering. So combination of 3D printing with tissue regeneration engineering. So that's going to grow quite a lot in the next decade. 3D scaffolds, of course, they're all interrelated with each other. Okay. So we make a 3D scaffold of vascular grafts using a biodegradable polymer. Then we seed the cells externally. When the cells grow, we insert it into human body. And after some time, the base material or the support slowly degrades. So you will be ending up with the scaffold from the cells. Okay, that's going to be the future. Blood-brain barrier penetration. Okay, so this is a big challenge. So if we want to design drug delivery systems which will penetrate the blood-brain barrier and reach the brain, we need to develop materials which can do that. As you know, there is a barrier which separates the blood with the the brain with the rest of the parts of the body. So when the blood flows, it allows only nutrients and oxygen to flow and reach the brain, whereas it doesn't allow viruses, large molecules, and since there is a blood-brain barrier which separates. And if you want to deliver drugs to reach the brain region, of course, we need to be very smart designing a drug delivery system which can penetrate this. Okay, so this again, pharmaceutical industries may be really interested to look at this type of research. Bone graft substitutes, especially large defects. If you have defects which are more than 4 inches gap, short defects, bone starts growing, but large defects, how do you address that? Either because it is because of certain trauma or because of certain defect, birth defect, then how do you address this type of situation? Currently, there are no real solutions for this. So they use a metal implant in that. Multiple drugs delivery. So I want to deliver 2 drugs. Like I said originally, a fast-acting antibiotic which will kill 90-95% of bacteria. Then a slow-acting, much stronger antibiotic which will kill the remaining bacteria, which may be more persistent or which may be more resistant. So multiple drugs delivery. Hydrogels, because hydrogels, aerogels, they are able to take in a lot of water, very highly hydrophilic. They are very useful in situations like wound dressing, wound healing situations, burn wounds. So there needs to be a lot of research, and that's where it is going to go move towards. Imaging, okay, a lot of imaging is one area. Can we have live imaging? Of course, there are certain microscopic techniques. A lot of microscopic techniques are there which looks at the material biological system interaction, but still live imaging based on photoacoustic or based on IR. I think that is one area that's going to grow quite a lot, especially for in vivo studies with animal models. Accelerate platelet aggregation, especially when the material is going to be used in blood region. It has to quickly get acclimatized. It has to get quickly approved by the blood region. Okay, so we want to accelerate the platelet aggregation. Nanotopography and metal. This is called biomimetics. Biomimetics came into being because the question was, why doesn't the fish get a biofilm on the surface? Okay, so that is because of their nanotopography. Can we design material with that type of nanotopography, either on metals, on polymers, so that per se there will not be any bacterial attachment, so that the infection can be prevented, or it enhances the cell attachment. So can we create those type of nanotopography on the surfaces of metals or polymers? So this is another area which will definitely be very interesting for the biomaterial researchers. Of course, these are related. Prevent biofilms. This is an endless problem. The first response, as soon as the material is placed inside, is if there are any bacteria, attachment of bacteria leading to biofilms, leading to infection, material rejection. So preventing biofilms is an endless war between the bacteria and the scientist. How to prevent biofilms, how to reduce the resistance strains developing. All these are big challenges for the researchers. Understanding interaction between biomaterials and biological systems. As soon as the material is placed inside, you are going to have inflammatory cells coming to it, bacterial coming to it, blood platelets coming to the material, tissues developing, and there is tissue which is going to engulf the biomaterial because it's an foreign object. So we need to understand the interaction. And this is a very, very important point we need to understand. Unless we understand, we will not be able to design different types of materials. Okay. So you have, after implantation, stress, homeostasis, immunoinflammatory response, and bone formation, for example, if it is an orthopedic or implant failure. So we need to understand the mechanism. Unless we understand the interaction between the biological system and the material, what happens, we will not be able to design these various types of biomaterials. We will not be able to address all whatever we have talked about. Okay, that's very, very important. So understanding this is a big challenge, actually. And that is going to be an endless work, actually. So there was a question on calcium sulfate. What type of calcium sulfate? Generally, calcium carbonate. Calcium carbonate, we should not be having any, calcium carbonate. Ideally, it should not be acidic. So that's very, very important. We don't want acidic calcium carbonate, which could lead to a local acidity and cell toxicity. So ideally, we should have neutral calcium carbonate. So acidity is a very important parameter which you need to look at when you are designing implants with calcium carbonate. Okay, there was one more question on implantable antennas for wireless biomedical devices. So I thought I will talk a little bit about that. Where do you use implantable antennas, especially pacemakers, defibrillators, glucose monitors, cochlear implants, drug infusion pumps, intracranial pressure monitors? So these are placed inside the body and they keep sending information outside, either to a clinician. For example, pacemakers keep sending signals to a clinician to tell him or her whether the pacemaker is working properly. Or a glucose monitor collects the information about glucose and sends information to an outside device saying that blood glucose is under control. So obviously, there has to be an antenna system for this wireless biomedical device. Okay, so there is a wirelessly exchange data with the exterior monitoring control equipment. So maybe just data is coming out, or from the data, maybe there is a feedback to the equipment to work in a different manner. So the antenna system plays a very important role in these type of situations, pacemakers, defibrillators, and so on. Generally, they are connected to a low frequency inductive links. Okay, that's what has been used. But there are many limitations of that. Low data rate, because exchange of data is very, very, very low. The distance of communication is extremely low. So the patient has to be quite close to the monitor exterior system. Okay. There could be sensitivity to intercoil misalignment. So they are not misaligned properly. There could be. So there is now more interest on antenna-enabled medical telemetry. They are trying to look at other ranges instead of 402 to 405. They are looking at other ranges so that we can improve the data rate as well as we can slightly improve the communication range. Okay. So low power consumption is a big concern because there are batteries which needs to be kept, especially in these type of systems. And then what will be the life of the battery? Because after all, if somebody has a pacemaker, it's going to be a lifelong. And so what will be the life of the battery? What do you think about charging of the battery? All those needs to be considered vis-a-vis the safety of the patients. So many issues are there. Many research directions are being looked at. Antenna dimensions, radiation efficiency, battery life, communication distance, polarization. So there is a lot of scope for engineers in these type of expertise to work on, especially on implantable wireless biomedical devices. Okay, so with that, let me conclude what I have been talking about as a summary. on this particular course, which is called Medical Biomaterials. We have looked at it in detail over the past 8 weeks, and I hope you were able to get a flavor of the interdisciplinary nature of this particular area, which involves engineers, scientists, material scientists, biochemists, biologists, polymer chemists to get involved. Of course, clinicians as well when you talk about animal trials or human volunteer trials. So it's highly interdisciplinary in area, and it's exciting area to do research, because my lab works quite a lot on orthopedic systems, and so it's quite exciting area to work on actually. And I hope you enjoyed the course, and I hope you were able to solve some of these quizzes. And the final exam is going to be exactly like this. The problems will be similar to that, so you don't have to worry much about get worried too much about it. If you are able to solve all the problems in the quizzes, you'll be able to solve the problems in the final exam also. So I hope you the best of luck in the final exam. I hope some of you take up biomaterials as your research career, and it's going to be an exciting area for biomaterials in the next decade or so. And of course, I will share these slides which I have presented in this particular live session for all of you to have a look at. Okay, all the best. Thank you very much for spending time with me. Can we have practical class? Practical class.